Chapter 11, Lesson 3. In this lesson, we'll take a look at something called the heating curve, and then something else called the phase diagram. Now, a heating curve essentially shows the phase changes through which a substance goes as heat is added. So usually heat is placed on the x-axis, sometimes time or progress is placed on this x-axis, and the temperature is placed on the y-axis. And what you get is you see usually 5 distinct regions of a heating curve. You first see the solid portion. In this case, because we're doing water, it is ice. The solid portion being heated. Then you see the solid melting into a liquid. Then you see the liquid portion being heated. Then you see the liquid becoming a gas, and finally the gas being heated. And sometimes these transition points aren't as clear and as essentially angled. Sometimes it's much more of a gradual change here. But for the sake of us seeing the different 5 parts, this will do. Now you'll notice that 2 things. During the phase change, solid to liquid and liquid to gas, the temperature stays constant. Now this is a very important feature, and this is true of any substance. During a phase change, the temperature does not change. This and this are flat lines. Secondly, you'll notice that the solid-liquid phase change is much smaller than the liquid-gas phase change. And that's because anytime you're converting a substance from a liquid to a gas, you completely break the intermolecular bonds. So here, bonds are completely broken. Because recall that gases do not have attractive forces, so you have to completely break these attractive forces. In the case of melting, bonds, you can say, are loosened. This is a term that's not very scientific, but we'll say the bonds are loosened. They're weakened, you can say. So you see those 2 features, as well as some others as we go along here. So this is what we just mentioned. The heat added to the system during the phase changes of melting and boiling go into pulling the molecules apart. So the temperature does not change, is essentially the idea. This, by the way, is also why canteens are usually, historically they've been leather, and more recently there's some sort of cloth on them. And the reason for this is because you dip the canteen into water as you're walking along your trail, dip it into a stream, and as that water evaporates from the canteen surface, that water essentially draws heat away from the interior metallic, which has the drinking water, and essentially it keeps your drinking water cool. This is a little trick, and we'll actually use this concept. So anytime a phase change occurs, there is a heat change associated with it, and we'll take advantage of this heat change to be able to calculate some heat that's been released or absorbed by a substance. So in order to do that, we'll use these 2 equations. You've actually seen this equation before. This was the equation we used to determine the heat of reaction of some sort of chemical reaction. And if you recall, it involved using specific heat, mass, and delta T. This is your MCAT equation that we've seen. So this equation you use anytime you're going through a diagonal portion of the heating curve, when you're heating the liquid, heating the solid, or even heating the gas. The second equation that we'll use has just 2 terms in it. It has moles and then something called heat of vaporization, which we'll take a look at in a minute. And this equation you use for the 2 flat portions of the curve. Simple way of remembering it, or a little elementary way of remembering it, is the equation that has 2 parts, in this case moles and delta H, goes with the part of the heating curve that has 2 sections, 2 flat lines. This equation, having 3 parts, goes with the 3 portions of the equation, or the curve that's diagonal. So we could take a look and ask a question something like this: how many grams of water can be cooled? This is kind of the canteen question. From 35 degrees C to 13 degrees C by the evaporation of 45 grams of water. And the heat of vaporization of water is given as 2.4 kilojoules per gram. and the specific heat is given as 4.18 joules per gram degree Kelvin. Now, what we're going to have to do here, essentially, is use the heating curve to do both of these calculations. So, if we take a look at the heating curve, every heating curve, we'll say, has these 5 sections: heating of the solid, melting, heating of the liquid, boiling, and heating of the gas. So what we're doing, effectively, we have water. So this is boiling, this is freezing. This could be said to be 0, and this could be said to be 100. So what we're doing is we've got one amount of water inside the canteen that will be cooled from 35 degrees Celsius down to 13 degrees Celsius. Or we're going to undergo a temperature change of 22 degrees. This would be our delta T. This is the water inside the canteen. So we can say in canteen. The second canteen, please, thank you. And the second amount of water is the one that will be essentially evaporated, because it says we're going to essentially evaporate 45 grams of water. So the other side of it is we've got 45 grams of water to be evaporated. So you can say, if this is your canteen, you could say that 45 grams of water on the surface will evaporate, and how many grams on the interior will we cool, is the idea. So what we'll do essentially is just apply the two equations. The equation, the first equation that that deals with evaporating of the water, is actually represented by this portion of the heating curve. So right here is where we'll be evaporating water. So if you recall, this is the two-part equation, the one that says delta H equals moles times heat of vaporization, something called heat of vaporization. And heat of vaporization is simply the amount of heat necessary to vaporize a certain amount of water or any substance that you're dealing with. So let's first use this equation. So delta H will be equal to, now we're actually given grams in this case, and we're giving kilojoules per gram for the heat of vaporization. So we can actually just as well use this equation to say grams times heat of vaporization in terms of grams. So it's easier to actually just go ahead and use the grams directly without having to convert to moles, as long as your heat of vaporization is also given in terms of grams. So in this case it is, so why don't we just dive right in. So we have ourselves 45 grams multiplied by a heat of vaporization of, let's try that again, which is 2.4 kilojoules per gram. So essentially, we're vaporizing 45 grams, and each gram requires 2.4 kilojoules. So multiplying the two, we require 108 kilojoules. Now, this 108 kilojoules will be pulled away from the water on the interior of the canteen. So we're asking then how many grams would that result. So we'll use the second equation, which deals with this portion of the heating curve, and that equation, if you recall, said that delta H, this is your MCAT equation, equals mass times specific heat, C, or S, times delta T. Excuse me. And so let's go ahead and apply that second equation. This will be our heat. Now we will have to convert this into joules because specific heat, C, is always given in joules. In fact, C here is 4.18, this famous number from chapter 5, 4.18 joules per gram Kelvin, or degrees Celsius. So let's convert from this to joules first, and this is simply multiplying by 1,000, so we got 108,000 joules. And so let's plug this into the equation. We'll use the equation that's delta H, the MCAT equation, equals M times C times delta T. our delta H is 108,000 joules, equals M is what we're solving for, multiplied by our specific heat, which is 4.18 joules per gram Kelvin, multiplied by our temperature change, which is 22 degrees Celsius. And essentially, rearranging the equation, we get ourselves mass equaling, we can just put it all together. Put mass on this side. Mass equaling 108,000 over 4.18 multiplied by, let's go and keep the units along here, joules per gram Kelvin, multiplied by 22. Now, I don't have to convert to Kelvin because 22 degrees Kelvin, 22 degrees Celsius is the same in terms of the change. So this does not need to be in Kelvin, necessarily converted to Kelvin, because the increase on the scale is the same. The absolute temperature is different, but the increase is the same. So let's do this calculation. We'll divide by 4.18, and that should give us 1,174 in this case grams, because we're solving for mass. So consulting significant figures, we had 2 sig figs to begin with, and so we'll probably have to keep it at 2 sig figs, which gives us about 1,200 grams. Whoops, 1,200 grams, or 1.2 kilos. How about 1.2 kg? 1.2 kilograms, which is essentially about a liter, 1.2 liter and a quarter, which is easily carried by a canteen. At least a liter. Usually you carry a little more than a liter with you. And that solves this sort of problem. We've essentially used the heating curve, 2 portions, 2 equations from the heating curve to solve a problem like this. We're going to try another one. And this next problem will be a little more involved in terms of using more portions of the heating curve. And here it says calculate the enthalpy change upon converting a mole of ice at negative 25 degrees C to liquid water at 50 degrees C. The specific heat of ice and water are 209 joules per gram Kelvin and 418 joules per gram Kelvin. And the heat of fusion for water is 601 kilojoules per mole. So if we take a look at our heating curve again for water that we've just drew, what we've got these 5 regions of the heating curve, and we've got 0 degrees Celsius in the bottom here and 100 up here. So what we're doing is, in this problem, we're beginning at negative 25. So say we begin right down here on the heating curve, and then we have to get up to 50 degrees C. So we have to end up right here on the heating curve. So we'll end up going through 3 portions, 1, 2, 3 portions of the heating curve. So let me go ahead and, because we'll have to use different equations for each portion, let's go ahead and label this portion A, this portion B, and this portion C. And essentially we'll just do it in that order. So first, let's use equation part A, and the equation here, because temperature is increasing, remember this is temperature on the y-axis. Since temperature is increasing, we'll have to use the equation that has the temperature term. So delta H in this case will be will be mcat, mass times C times delta T, which in this case, our mass, if you take a look, we have 1 mole of ice. So let's take a look at that, 1.00 mole of ice, which is H2O. So converting from grams to moles, we know that a mole of water is about 1802 grams of water. So really we got 1802 grams. This is essentially the molar mass of water. So that is the mass that we'll put in for MCAT. So we got 18.02. Then our specific heat, as usual for water, is 4.18 joules per gram degree C. And then finally, our temperature change is from negative 25 up to 0. So the delta T in this case is actually you can say final minus initial, so 0 minus negative 25, essentially you get 25 degrees. And that's how we got our temperature change. This is 25 degrees Celsius. So if we multiply those three numbers together, we will get ourselves a fine value. So go ahead and plug these in. 4.18 and 25. And this gives us 1,883 joules. So we'll keep this for now. Let's go on to part B. Now in part B, we're melting the ice, so we'll use the equation that says delta H is moles times heat of fusion. And heat of fusion is how much heat it takes to melt ice times heat of fusion. In this case, we have exactly 1.0 moles of ice, and our heat of fusion of ice is given to us as 6.01 kilojoules per mole. So that will be 6.01 kilojoules per mole. So if we multiply these two numbers, essentially you get 6.01 kilojoules. Let's go ahead and put this into joules right away. It turns out we'll have to convert all three of them to the same unit. So why don't we say that this is the same as 6,010 joules. To melt the ice, this is how much heat it takes to melt the ice. And finally, in part C, what we'll do is we'll have to heat up the liquid water now. So again, we'll use the equation, the first equation, and the MCAT equation. That should be a C. So plug and chug, and we got ourselves the mass as before is 18.02 grams. The specific heat of water is 4.18 joules per gram degree Celsius. And now I see that I made a little blunder here, because in fact when we used the number before for ice, the specific heat of ice is different than the specific heat of water, so these cannot be the same. The blunder that I made is we'll have to recalculate. This is the wrong number that I put in for ice, because the heating up ice and heating up water, the molecules take energy in differently, so the specific heat will be different. But let's finish this up first, and then we'll fix the ice portion. And so we've got ourselves 50 degrees Celsius, because we're heating for a temperature change, because we're heating water after the boiling point up to 50, and because recall that this is where we're trying to end up at. So multiplying these three numbers together should give us a fine value of, go ahead and multiply them through, 3,766 joules. Alright, let's go back and quickly recalculate our value here. Turns out we're going to have to use the specific heat of ice, and this will give us a different total. So if you take a look at the problem, the specific heat of ice is 2.09 joules per gram Kelvin. So we'll have to use 2.09 in here, 2.09. So that multiplied through gives us a different value, and that value, if you multiply it through, get 18.02 multiplied by 2.09 multiplied by 25 gives us 941 joules. Really we'll say 0.5 joules. And now we can go ahead and add all three of these up together to know the total heat that it will take to heat up ice up to the 50 degree mark. So total, you can say delta H total is, let's do 941.5 plus 6,010 plus 3,766. Now right away you'll see that it takes quite a bit to actually melt, quite a bit heat to melt the water. Really the biggest number out of all of these is the melting of the water. which makes sense. So if we add those up, 3766, we should get ourselves a fine value of 10,717 joules, which in kilojoules, and since we have three significant figures for our numbers, so we'll say 10.7 kilojoules. kJ, and this would be essentially our final answer, depending on the unit that we're asked about, but 10.7 kilojoules. So we'll work a few of these out on the web assign, and hopefully you enjoyed this, lesson 3 of chapter 11.